estimation. So let us see this on the following slide. All right, so this is basically the the derivations we did. So here it is, the next slide. So imagine that you sample 2 data points at a time. So think of experiments A, B, C on these pictures from the true Gaussian, which is that green curve that you see marked as true Gaussian in this picture. So you do MLE estimate in all 3 experiments using the blue data points, so 2 at a time. So the mean and the variance you computed. The variance again is with respect to the sample mean, and you can immediately see that in each case the sample variance is underestimated versus the variance of the true Gaussian. Now you may say, what happens if I average the results on the 3 experiments? And you see that the MLE estimate for the mean looks pretty good. Basically, it will bring you very close to the mean of the true Gaussian, but the MLE estimate for the variance is basically, I look in the 3 cases, it looks basically the same in cases A, B, and C, and it is significantly less than the variance of the true Gaussian that you see under the green true Gaussian case. So this is indeed what the problem is with MLE in the case you have limited data. If you have lots of data, of course, this is not a problem, and MLE can be a decent statement, a decent estimate of your parameters, but you need to be sure, nevertheless, that your estimate can operate on whatever data is provided to you. All right, so I want now to make a connection between these maximum likelihood estimates and something you already know from previous courses in your studies, and in particularly what is called weighted least squares methods. So I'm going to try to design an example where popular basically with weighted least squares, but also useful later on in the course in the context of what's called model reduction. So let's consider that we have a multivariate Gaussian, as you see it on the top, and we take the mean of this multivariate Gaussian to be unknown, but we take the variance gamma to be given. Okay, so we don't have to deal with that complexity. Now we will assume that we collect data from this distribution, data X, and I want you to think of this data X as approximations basically of the mean X0. This is really what we try to compute. We try to compute the mean X0, and what I'm going to do is, because X and X0 are high dimensional vectors, we're going to do some sort of approximation, a model reduction if you like approach, and I'm going to assume that X0 depends through the equation that you see, the second equation, through some vector of hidden variables Z, and we're going to assume that the dimensionality of Z is much less than the dimensionality of X. So we're making a model, and we say, rather than computing X0 in, let's say, 1,000 dimensions, maybe it would be sufficient to compute Z in let's say in 50 dimensions or in 10 dimensions. Okay, and we assume for now that this matrix A is known. So this setting up with hidden parameters, it will be very typical later on in the course when we discuss about model reduction. So what's our problem now? The problem is, given samples of X, we want to come up with an estimate of Z for a given A. Okay, again, given samples of X, we need to compute some point estimate of Z, and the data X are coming from the distribution that has a mean X0, which is AZ, and a variance gamma. So we need to be able now to write down our likelihood function, right? So we want to compute z, so we need to be able to say something about the probability of x given z. Okay, that's what the likelihood model is. Z are a known variable, so we need to be able to say something about the probability of x given z, and of course this is defined by the model error, that in this case is the variance gamma that we have in our Gaussian model. So what is the mean and the variance of x given z? Can you look at the equation on the top and try to think on how we compute the mean and the variance of x given z? How do we do that? So if we have given z, right, can we compute the mean of x? Can we agree because that the mean of x is basically a times z by our the setting of our model? All right, so let's see on the next slide. If you don't like that, how about if you write our model explicitly as x equal a times z plus some noise, some additive noise e that comes from a Gaussian with mean 0 and covariance gamma. All right, so can you see now directly that the mean of x is basically az plus the mean of e, which is 0. So basically by design the expectation of x is 8 times z. Similarly, if we compute the covariance of x by substituting our model from the first equation, we can immediately see that the covariance is the same as the covariance of the noise z, which is our given gamma, again specified for this problem, taken as given. So obviously we have a Gaussian distribution for the likelihood, and in the next equation we're going to see this Gaussian for this additive model case written explicitly. So you see that the probability of x given z is the Gaussian with a mean az and a covariance gamma. So let's go back to our problem now. We collect some samples of x. Let's denote those x1, x2, xn. So these are samples that come from this additive noise model, and from these samples we want to estimate our unknown z. All right, so we're going to do this by using maximum likelihood estimate. So we need to compute our likelihood for this n-size data set, and then we need to find the maximum of the likelihood or of the log likelihood with respect to the unknown parameter z. So let's see, how does the likelihood looks like if I collect 10 data points, right? We know on the equation you see for one data point. So what we need to do is, assuming that we sample this x's independently from each other, we can write down that the likelihood function will be basically the product of the likelihood of each of these data points. So pi of x1 given z, pi of x2 given z, etc., until we have all of our data points basically included in the likelihood calculation. So if you look at the exponential, when you multiply these terms together, you will basically get in the likelihood you will get a summation in the exponential that has each term for one of the data points,